morning, everybody. Welcome to the Itasca What's New in FLAC2D 9 webinar. Today, we have two presenters, Andre Pachigoretz and Derek Blacksma. They will be speaking to you about FLAC2D 9 and all the exciting new features and changes that have been implemented. Andre is Senior Software Engineer and the FLAC2D Product Manager, and Derek is a Software Developer and Geomechanics Engineer. My name is David Dugagne. I'm a Senior Engineer in Technical Marketing, and I'll be the organizer for today. Next slide. So we will have an opportunity towards the end of the presentation to answer questions. So throughout the presentation, if you have a question, just use the GoToWebinar dialog. You can see what the question area is, and you can just type in your question and hit send. And then at the end of the presentation, we will go through as many questions as possible. If we don't have a chance to finish answering all the questions during the live event, we'll follow up with you on answers.
Well, good morning, everybody. Andre Pachigoretz is here. I will continue the presentation, and also Derek Blacksma gonna join in and talk about a few features of FLAC2D. First, we're gonna start with a few slides about what is FLAC2D, what its applications, a little bit about some history and background information. For those people who never used Itasca software, and particularly FLAC or FLAC3D, FLAC2D is very similar to those codes. And I just would like to mention what it is about and few general applications among variety of applications where it can be used. FLAC2D is a computational software for modeling and analysis of displacement, stress, and stability of soil, rock, and structural support in 2D. This is very short description, I would say quite incomplete description of what FLAC2D can do. But it highlights major features of FLAC2D. And among major applications where FLAC2D can be used is tunnel stability and support, surface excavations and foundations, slope stability and stabilization, embankments and dams, and many, many others. People who are familiar with our other software probably know that it's a very versatile software that can be applied for a variety of different applications, which of course I cannot put all of them on this slide, but we're gonna mention quite a few throughout the presentation. The history of FLAC starts more than 40 years ago. Itasca flagship finite volume software FLAC was released almost 40 years ago, and here we refer it as finite volume, but in application to 2D. And in the beginning, we refer to it as finite difference, but really it's based on finite volume formulation. FLAC is widely used in geomechanical analysis, and it's often used for rather complex analysis like highly nonlinear deformations, dynamics, large strain analysis, and so on. And here on the right, you can see original manual from 1986 for FLAC version 1, and the original FLAC version 1 on, I believe it's IBM i386 computer, one of the first laptops. So you can see that FLAC has very long history, very successful history, very proven history and track of applications. And basically, we're building FLAC2D on all this history and all the power and strength of all different versions of FLAC. So why are we actually switching from FLAC, previous versions of FLAC to FLAC2D? First of all, FLAC2D is a major overhaul to modernize the classic FLAC program, and it's a successor of FLAC 8.1. However, FLAC2D uses FLAC3D platform and assumes plane strain conditions, same as FLAC 8.1. FLAC2D is built and lives within modern Itasca framework, which is the same as for FLAC3D, PFC, and FreeDEC. And this framework provides consistent user experience as well as advantages in code development. Basically, it's enormous unification between the codes. And now FLAC2D can use all the advantages of common framework and different modules that are available in FLAC3D, PFC, and FreeDEC. What will happen with previous version of FLAC? This is probably important for people who are very familiar and who have been users of FLAC 8.1 or earlier versions. So FLAC, previous versions of FLAC will stay at current version 8.1, which will be supported and updated, though mostly bug fixes, and it will be updated until 1 year after FLAC2D version 10 is released. So basically, we will continue in support of FLAC 8.1 while adding all the remaining functionalities and features to FLAC2D, and obviously adding new things as well. So FLAC 8.1 is still around, it's still supported, but users of FLAC 8.1 are encouraged to at least try and hopefully switch to FLAC2D version 9 and later use all following versions. Another question that people may have is why using FLAC2D versus FLAC3D when certain models can be built with FLAC3D? First of all, let me mention that FLAC2D is based on plane strain analysis. And here's an image. Let me see if I can get the pointer. Here's an image of what plane strain analysis is about. Essentially, we assume infinite out-of-plane domain in which out-of-plane strains are 0. So that's a simplification from full 3D analysis. And this makes FLAC2D significantly faster than FLAC3D. So basically, if you run these two similar models in FLAC2D and FLAC3D with appropriate boundary conditions, FLAC2D will be faster. And I will show later how much faster. FLAC2D is also simpler to work with when operating with 2D geometries and models. And FLAC2D is cheaper than FLAC3D. These three factors are probably the major difference of why people would choose FLAC2D versus FLAC3D, even though both software look very much alike and feel very much alike. Now, what's the difference between FLAC2D version 9 and FLAC 8.1? As I mentioned, FLAC2D uses the same user interface as FLAC3D. FLAC2D uses the same logic for project data file and save file management as FLAC3D. And commands and fish in FLAC2D mimic FLAC3D style. And in most cases, they are exactly the same. So these are probably some of the major differences that people are gonna see when switching from FLAC 8.1. FLAC2D will feel and work very similarly to FLAC3D. One other very important feature of FLAC2D is that it does not use IJ space. People who are familiar, or users who are of FLAC 8.1 are very much familiar with what IJ space is. Any geometry in FLAC 8.1 or earlier versions is represented in a structural grid in so-called IJ spaces shown here. And all the operations with the geometry, with the model, have to be done using IJ indexes, or most of the operations at least. In FLAC2D, this is not the case. You essentially just create geometry of the model as needed using regular coordinates. Then you can group certain objects within this geometry, and you just operate on these objects or use coordinates directly. This allows using not only structured meshes, as shown for FLAC 8.1, but a combination of structured and unstructured meshes, or just unstructured meshes, or any other combination, what is more suitable for the model. And you can see here that we can refer to groups of objects, for example, grid points, by using so-called grouping logic, which is the same among all Itasca Common Framework codes, FLAC3D, PFC, FreeDEC, and now FLAC2D as well. For those who are not very familiar with FLAC2D or haven't used it yet, there's a quick start tutorial available in documentation, and you can easily get to the documentation through its web page, which is docs.itascacg.com. Then this is the first thing that you're gonna see when you click on FLAC homepage. And from here, you can go to tutorials or new user guide or example applications or commands, and basically look through all this material and familiarize yourself. Alternative way how to get to the documentation, if you go to help and in FLAC2D and then click on help and documentation, a local copy of documentation will open for you. A local copy is installed when you install in FLAC2D or Itasca software in general. And then you can see all the same things there. It's just going to be locally on your machine, and you can see it through FLAC2D interface. So the best place to start is tutorial quick start, and you can always refer to it through this slide. All right, now we're going to talk about more specific features of FLAC2D, what's new, what's different in FLAC2D, and we're going to cover multiple topics here. We're not going to go into significant level of details on each topic. We're rather going to show all major features of FLAC2D and what can be done with these features. And if there's any significantly different features from either FLAC 8.1 or FLAC3D, I will mention them as well. So we'll start with new user interface. With version 9 of Itasca software, we had a relatively significant overhaul of user interface. And now user interface has relatively organized, I wouldn't say strict, but very well organized structure, in which we have on the top a main menu with different menu options. On the left side, we have a project pane, which organizes all the project information like data files, plots, save states, sketch sets, geometry sets, and so on. In FLAC2D, only sketch sets are present though. Then we have a command console, which hosts the information of all the inputs and commands that's being typed in FLAC2D. Also here we have Python console, information about fish symbols, and state record, which records every operation that user does in FLAC2D. Finally, we have content workspace, which can be shared between data files, plots, sketch sets, and other tiles that can contain modifiable information. On the right side, we have contextual tools that change depending on what is active currently. For example, for plots, you will see all the operations or all the modifications that can be done to plots. And also you can see a help system here. So there's help panel available. When you click on F1, this pane will be substituted with the help pane. Finally, we have a layout of toggles and status bar, so you can quickly switch on and off any of these panels here. And I will have a short demo after I'll go through next few slides, so you can see how this UI operates. We also did quite a lot of improvements in building model. And now model is, it's easy to build with a tool that we call Sketch. So essentially you sketch your model first in this tool, and then you generate zones out of sketched model. So Sketch has powerful tools for model construction and meshing. And here you can see an example of how a model can be built in Sketch with a variety of drawing tools that's available in this panel. Here you can import background geometry such as DXF files, STL, or raster graphics, and then trace this geometry to create your model. You can create geometry by free drawing using a number of tools available through the menu, sketch menu here. You can easily create tunnels or slopes or dams using a couple wizards that we added. You can also easily create structured and unstructured meshes pretty much by one click. You can assign groups and edges to zone blocks. A block, it's essentially a polygon, closed polygon. So as long as you have a closed polygon, you can create a mesh within it. We have background grid here. We have rulers. When you create your geometry, there's snapping options available to background geometry and also background grid. As I mentioned, you create zones or mesh by press of a button. And finally, when you generate zones out of Sketch, FLAC2D automatically switch to so-called model pane, where you continue modifications of your model if you desire so. For example, to assign a constitutive model, to assign material properties, to assign additional groups, and so on. Alternatively, if you don't want to use model pane, you can directly switch to a data file and continue model creation through a data file and commands or fish or Python. So a few words about the model pane. So model pane is designed to work on generated zones and faces. And here we refer to faces as edges of 2D model. In reality, if you remember, FLAC2D is a plane strain analysis. So in out of plane direction, or I can say out of screen direction, it's an infinite plane, which is represented by an edge in 2D. So if you see an edge here, for example, the outside edge of this model, we will call it a face, which is very much consistent with FLAC3D terminology. That's why we decided to use this wording to not create any additional confusion. So here you can see that we can show zones or zone faces. And I will show this in a short demo. What can be done in model pane is you can automatically detect model boundaries and assign appropriate group names. You can manually select and assign or change zones and face groups. I will also show this. You can densify selected zones. You can assign constitutive models. You can set or load or save material properties into material database, as shown here. You can interactively create structural elements at selected zone faces, and the same for interfaces, though properties have to be assigned later through commands. We will continue working on further improvements of user experience by adding more and more operations to model pane and to Sketch to make model generation easier. Finally, before showing a short demo, I wanted to mention that we have a very powerful editor in FLAC2D, which is shared between all common framework software, Itasca common framework software. This editor allows syntax highlighting, line and block selection and editing, commenting and uncommenting, code and line folding, contextual inline help, ability to run and execute the whole data file, or only selected lines of code. You can also do, FLAC2D also does automatic saving of data files when you execute them, and also does periodic backups. And you can use commands, fish and Python within the same file. Even though if you use Python, the file has to have extension .py. Finally, talking about user interface, we had many plot improvements in version 9. For example, we have more attributes of contour plots, including user-defined contour ramp, as shown here. You can modify format and precision of contour legends. There's now an option to swap axes for tables and profile charts. Also, there's option to add minor grid lines to charts, improved logarithmic scale for charts. This is very useful option to omit past states when plotting yield states. And in general, more options for contour plots and histories. So with this, I would like to show how the user interface looks like. This is one of the examples that I already showed on one of the slides. You can see that user interface consists of multiple tiles shown here, and multiple sections of the screen. For example, project section. This is our main working area, console section, and I would call it information of modification section. So before going into each section, I can show how you can maximize or hide particular section. For example, now my working area is in full screen. I can modify it like this, but just by hiding different parts of the user interface. Everything is, you can move, you can change the size. You can split tiles now. For example, if I want to add another tile here, just to have another plot on the right, I can easily split. Say I want to have plot on the right, and here I can put any other content that I have available, for example, a set. You can see that it appears here, even though it's a little bit small and probably not going to be convenient to work with. I can maximize this window by closing other windows. As I said, I can change its size, for example, something like this. I can close this window, for example. And basically, you can customize your screen as much as you want. Also, whenever you click on a particular tile, depending on the type of the objects that are there, corresponding menu appears on the right side, and you can, for example, edit different parameters here. This is for sketch parameters. This is for plots. We can see number of plots here. And talking about plots, we have a variety of plots available in FLAC2D. You can see that there are a lot of different plots available. And if you have PFC license, you can add PFC plots here as well. Finally, I wanted to mention the help system. If you click on help and documentation here, it appears on the right side, and you can see that it's the same image that I showed on one of the slides, and you can basically navigate through help without exiting FLAC2D. Now, if I go to a data file, one important feature that I probably forgot to mention, let me switch to a data file here, it's contextual help. For example, if I type a command here and then press Control space, I can see that all commands that are available for this particular keyword will appear here. For example, zone, let's say zone property command to assign material properties. And now it tells me which material, for which material model I can assign properties. And the same is available for console line. Zone, I press Control space, and I can see that contextual help appears here. For example, grid point, and I can just continue selecting whatever is needed. For example, zone grid point fix for pressure, and so on. So this is very useful for those who are not very familiar with commands and syntax in FLAC2D or FLAC3D. And you can easily see which commands are available just by start typing some of the commands. I believe this is not, this contextual help is not available for FISH. So for that, you would need to click on FISH scripting, for example, and read which FISH commands are available for FLAC2D or general framework. So this is general review of the interface. Now let me start FLAC2D from scratch and run very simple model so you can see how FLAC2D, how it's easy to create reasonable models in very short time in FLAC2D. So I'm gonna start FLAC2D with no project. And first what I'm gonna do, I'm gonna load background geometry from a DXF file and automatically create a geometry out of this DXF. But before creating geometry, I would like to assign zone size, or which will be defined by edge length. Let's say we want 2 meters zone size throughout the model. And now I can automatically create all edges throughout this zone. But let's say I don't want this tunnel here. This is a toy model. And what I'm doing here is just for illustration purposes. So I can simply select all the points and create my own tunnel using Tunnel Wizard. Let's say we want this vertical wall arch roof type tunnel with some different parameters. And I'm going to create it slightly away from this geometry so it automatically doesn't intersect the geometry. So over here. Now I can select it and drag it to this to locate instead of my other tunnel. So now background geometry is not needed. I can simply delete it. Now I want to increase. By the way, you can see that if I select grid points or select points first, then all the selection works only on points. If I select edges, the selection works on edges. Let's say I want to increase discretization or refine the model. I just change it with zone length. And I can also assign groups here. For example, later I want to create liner along this geometry. So I set group liner here. And then I don't even need to specify which boundaries are set to be liners. I can just refer to this group. Now I can do automatic meshing by going through here. I'm going to do unstructured mesh and just click on select create mesh now. So mesh is created. Here I'm going to create zone group tunnel. And the model is ready. Now I can create zones out of it. So I click on the button, create zones, and it switches to model pane where zones are created. Let me change a few colors here. Just put some different colors so we can easily distinguish. Here I can assign boundaries to the model or group boundaries. I can assign material properties and constitutive models. So let me show first how to assign group names to the boundaries of the model so we can easily set boundary conditions later. For that, we can click on this button, assign groups, and now we have numerous different groups available. Actually, before I forgot to select one option here, ignore existing groups, so it's easier. And now we have fewer groups here. And you can see that on the left side, it's group west, on the right side, it's group east, and we still have tunnel or liner group here. Now we can assign constitutive models to the whole model. For example, more Coulomb model. And we can assign properties to different parts of the model. And this can be done one by one by set material properties, or I can load material database. A material database is user predefined database of properties. For example, I have material database with rock properties that I want to use here, and I'm going to import it to our current model. And then I'm just going to use these properties. So I'm just going to select different parts of the model and assign properties to the model. So for example, soft rock on the top and hard rock on the bottom. And these properties are somewhat randomly chosen. It's not, it's somewhat artificial example. It's just to show the operations. So after this, I would like to save my project and the save state. So I can return to this save state whenever it's needed. So I can save project. For example, I'm going to call it my project. And it offers to save the state. I'm going to call the state geometry and properties. So you can see that save state appeared here. The project is saved. And now I can continue working on a data file to apply boundary conditions and initialize stresses and actually run the model and excavate this tunnel. So I'm going to split my panel to the left. I'm going to create new data file. I'm going to call it main. And usually data files start with model new command. Then I'm going to restore the existing data file, geom prop. I'm going to set that large strain to off. So I'm going to run a small strain analysis, and I'm going to set gravity to 10. After this, let me copy a few lines of code that sorry, this is the wrong one, that I already have written to assign boundary conditions. For example, the command zone GP fix velocity at the group bottom, and I can see where my group bottom is. It's this group. And on the left and right side, I will have roller boundary conditions, and it's east and west groups. Then I'm going to initialize stresses with zone initialize stress command using specific ratio, and I'm going to solve after this and save the results in model save ini. But before doing that, let me create a new plot so we can see how the stresses change. So I'm going to put zone and contour, let's say stress, vertical stress. And here I'm going to create another plot, and we're going to track displacements here. Yeah, this is good. So we can execute the data file. I can just press execute here. We can do volumetric averaging. So we got some initial distribution of stresses and displacements, and the model is in equilibrium. However, before excavating the model, we need to reset the displacements, ideally velocity and state as well, if there's any plastic deformations happening or plastic failures. And finally, we want to excavate the tunnel using zone relax excavate command. Please read about this command in the manual. It's the command is gradually reducing strength of the materials to be excavated, density and stresses, and it's designed to prevent any spurious inertial effects happening when suddenly removing the material in the model. So I can select these lines of code and just say execute them, run selection, and now we can see that my tunnel got excavated, the stress distribution changed, the displacement distribution changed. We can see that there's convergence happening. We can add vectors of displacement and see where the convergence is happening. You can see that the bottom, the floor of the tunnel is converging faster than the walls of the tunnel. After this, the model is saved, and pretty much this is full example. You can see that in 5 minutes, I ran the whole example from scratch. It's pretty easy to build it. It's very easy to mesh the model, and you get results very quickly. Let me get back to the presentation and make a few other notes about the operations and solutions. In general, we improved how the static and dynamic analysis are executed. They got a bit faster because we did some optimizations on convergence criterion. Saturated fluid and thermal calculations also got really much faster by introducing new and better implicit solvers. I will talk about them a little bit later. If you run dynamic analysis, there is a new option for Maxwell damping. Derek will talk about it a little bit later. Plotting got faster. There's multi-threading in plotting that allowed plotting to be almost 10 times faster in FLAC2D and FLAC3D. We multi-threaded some additional commands more improvements in save and restore models. It's faster now as well. And we introduced more fish splitting and operators. Derek will mention this as well. When compared to FLAC3D, FLAC2D runs 2.5 to 3.5 times faster. This is mostly because of internal structure of zones that's used in FLAC2D. Factor of safety analysis run 3.5 to 4.5 times faster in FLAC2D compared to FLAC3D. And similar numbers are available for axisymmetric analysis in FLAC2D, even though it's right now implemented only for mechanical module. When compared to FLAC, it's a little bit trickier to see exact speed up because there's different convergence ratios implemented by default in FLAC2D and FLAC. However, if you just use model solve command, the runtime of FLAC2D will be smaller than FLAC. Essentially, FLAC2D will run slightly faster on average. So I would say the results are relatively comparable or faster for FLAC2D. The only difference is that FLAC2D uses stricter convergence ratio. So you will get more accurate results while running at the same time. FLAC2D also allows people to use a discrete fracture network, and it provides an efficient tool to generate and manipulate fractures. With discrete fracture network, you can generate the deterministic and stochastic fractures. You can determine intersections between fractures, fractures and user-defined geometries, and so on. You can compute clusters and connectivity properties, simplify fractures, define mechanical properties of fractures, obviously visualize them, and you also have Fish and Python access to fracture network. Here is an example of UCS test of a block containing 35 random fractures. And you can see when the material starts failing, the failure is happening along predefined fractures. And you can see that we already went over the peak, and material is mostly failing along this line where most of the fractures are. So this is something that you can simply do using discrete fracture network and without creating any additional geometry. FLAC2D allows people to use interfaces, same as in FLAC3D. So we have traditional FLAC3D style interfaces. They are single-sided though. They're characterized by Coulomb sliding and tensile and shear bonding. You can plot and track state of the interfaces, for example, normal and shear state. We also introduced zone joints in common framework, and FLAC2D has them now, but they're not fully documented and tested yet in FLAC2D. So I would say it's work in progress yet. The good thing about zone joints is that they are two-sided. They allow much more precise calculations when multiple interfaces intersect in each other. And this logic is similar to the logic provided in UDEC. So in the coming updates of FLAC2D, we will complete all the testing and documentation of zone joints, and people will be able to use them. FLAC2D enjoys 23 built-in mechanical models. You can see all of them here. And models with blue asterisks are improved models. Models in green are models that are new in comparison to FLAC 8.1. And models with 2 asterisks are completely new in version 9. Also, we have user-defined models. 3 of them are currently available. It's PM4 Send, PM4 Sealed, UBC Hist, and UBC Send is currently in progress and will be available hopefully soon. We expect within the next few months. So a little bit more details about new and improved models. First, it's pH model. There was a problem from previous algorithm by bands that people could experience when doing hysteretic loops. Basically, when you coming back from hysteretic loop, it was overshooting with shear stress, basically didn't go to the original path. New algorithm brings the path when you do hysteretic loop of unloading and reloading back to the original path. And this is very useful for dynamic analysis. Obviously, if you didn't get back to the original path through multiple cycles of loading and unloading, you could get potentially incorrect results. Now the results are much more accurate, and this is proven here through different examples. We also have improvements in ubiquitous anisotropic model. In particular, we allow more Coulomb failure in the matrix. Previously, it was only anisotropic elastic. New model von Mises with optional kinematic hardening. It's suitable for metal-like materials. And new interesting model, it's a plastic damage concrete model, which is based on damage mechanics and accounts for fracture energy within concrete. Here's an example of concrete beam, which is actually would be represented by an infinite plate in plane strain analysis, which is reinforced by cables, which are connected at the ends and have grouted in between the ends of the cable with certain shear stiffness assigned to the grout. And here we run 4-point bending test, and here you can see the video of how this test runs. We can see that cracking starts at concrete at the bottom of this slab, somewhat propagates, but complete fracture and failure of this slab is resisted due to presence of the cable. But at some point, fracture is happening. It's going to happen right now, and we can see that forces on the top drop because this slab got basically fractures appeared at the ends here. This model also allows for modulus degradation, and it has compatible more Coulomb yielding criteria. Finally, I wanted to mention factor of safety analysis before switching to a few other modules. FLAC2D has powerful factor of safety calculations with model factor of safety commands. It uses strength reduction method, which is in conjunction with full dynamic time marching solution, provides exact boundary between stable and unstable states. So it's much more accurate than any other approximate methods like limit analysis or limit equilibrium or method of slices, because it really runs full solution to find where the material fails and what would be the appropriate factor of safety. This command automatically applies to more Coulomb, ubiquitous joint, and Hooke-Brown models. It does automatic bracketing to progressively reduce strength properties until failure state is reached. Users can specify which properties to include or exclude. For example, you can run analysis of factor of safety considering tension failure, for example, for tunnel roofs. You can account for interfaces presence and also reduce their properties like cohesion and friction. You can specify accuracy, resolution, and other properties. And you can create factor of safety contours as shown here, which will provide information of different factor of safety values at different positions or different locations in the model. Fluid module in FLAC2D is classical FLAC3 style fluid logic, implements classical FLAC3D style fluid logic, and it's often used for simulation of effects of consolidation, seepage, liquefaction, and other effects. This is though single-phase fluid flow. This is one thing that we haven't implemented yet or transferred from FLAC 8.1, which also has two-phase fluid flow. However, there will be improvements coming in future versions of FLAC2D with regard to this fluid logic, which will make it easier to simulate two-phase fluid flow. Here are some outlines of fluid flow logic, and one of the highlights that I wanted to mention is that we have new implicit solvers such as precondition conjugate gradient or direct sparse solvers, which allows speed up of between 10 and 100 times. However, they work only on fully saturated fluid flow. and if you use implicit solvers, you can easily use these ones. There's a good description and documentation about how to use these solvers. And here are examples of what you can plot when using fluid logic, like phreatic surface, fixed pore pressure conditions, discharge vectors, and so on. With regard to optional modules, we have thermal and creep modules. Thermal module, it's pretty much the same as in FLAC2D, with the addition of same implicit solvers, preconditioned conjugate gradient and direct solvers, which allow for speed up of between 100 and 1,000 times for thermal calculations. This is very useful when you run very long analysis. For example, in nuclear waste analysis, sometimes you need to run them for thousands of years or hundreds of thousands of years. And these solvers significantly speed up any operations. In general, thermal logic is often used for transient heat conduction and related mechanical effects, or advections and related fluid effects, or hydration of concrete, for example. We also have 10 creep models to simulate creep behavior of materials, which range from classical viscoelastic models to viscoplastic models that often used in nuclear waste analysis, for example, WIP salt model. With this, I would like to switch to Derek, and he will continue with description of dynamic module.
So briefly, FLAC2D includes a dynamic option. Dynamics includes liquefaction modeling. Another important aspect of our dynamic module is our damping options, which include local, hysteretic, Rayleigh, and Maxwell damping. Maxwell damping is a new feature in FLAC2D. It addresses some of the shortcomings of the Rayleigh damping. For example, Rayleigh damping had a tendency to severely affect the time step in models with varying size zones. Maxwell damping addresses some of those shortcomings. Another improvement to our dynamic option is multi-stepping, which is a routine that benefits large models with varying size zones and reduces the calculation time for those very large models. Dynamics is also included for our structural elements, which I'll talk about in a minute. And then lastly, we offer a dynamic input wizard, which gives users the ability to filter and do baseline corrections to their dynamic histograms and accelerations. And then I also wanted to mention for our dynamics, we have a very in-depth number of tutorials that teach you how to use the different types of boundary conditions, and also it teaches you how to do the different types of damping. To include a number of examples, such as for dams, how you can do dynamic analysis for mechanical or hydromechanical coupling. And then also a popular topic for dynamics is liquefaction, and we include a number of examples for liquefaction. And then over here on the right is a brief video I'm going to show where this is actually a wharf. It's a platform supported by two pile elements that is being shaken from side to side. And it's recording the displacement at the top and the bottom of the model. So this is something you can do with our dynamic option in FLAC2D. Okay, moving on. My next topic, I'm going to discuss our structural elements in FLAC2D. In FLAC2D, we have four main types of structural elements. They're called beams, cables, piles, and liners. We also include a structural element called block bolts. They're an extension of piles, but they're not one of the main structural elements we have in FLAC2D. Our structural elements have a very robust element to grid interaction, which we call links. You can link your structural element to the grid in a variety of ways, depending on what type of element you're using, a pile or a liner. Also link different types of elements to each other. So you can link a cable to a beam or a cable to a liner. This allows you to create a very complicated model using these different elements. Structural elements are actually a plane stress element. However, you can have the option to define spacing and out of plane spacing at 1 meters, 2 meters, or whatever unit you wish. We also include in our elements an embedded element. An embedded element allows you to create either side of the element. This might be useful, for example, if you have a wall that's dividing two different types of material. On one side, you might want different properties between the links than on the other side. As I had mentioned, our structural element logic includes dynamics and the thermal option. I should say the thermal option is under development and will be released later. Our structural elements are also FISH and Python capable, and the Python capability is under construction as well. The image on the left, or excuse me, on the right, is just kind of a toy example showing on top the different types of linear elements. So on the far left we have, let's see if I can get mine. Maybe pointing. We have beams, and I got supporting open excavation, cables inside the material, and then a pile wall. And then below this model is the liner elements, and they're lining, such as something like shotcrete in a tunnel. So just real briefly, I'm going to talk about some of the applications for these structural elements. So beams are our most simple element. They are rigidly connected to the grid. They're often used for braced excavations or rigidly connected walls. Braced excavation would be the simple example down on the left. Cables are a little more sophisticated element type. It's often used for soil reinforcement, pull-out tests, and tunnel support. For example, here's an oval-like tunnel, cables embedded in the soil, and it's showing the contour of the axial force on each cable. The last two structural elements in FLAC2D are piles and liners. Piles are an element that is often used for soil reinforcement, and bearing effects, and foundation support, such as the wharf example video that I showed. And then lastly, liners are a little different than the last three elements I talked about. Liners are formulated to be continuous out of plane, much like a continuous wall. And they're often used for tunnel lining, such as shotcrete, and they're often used for walls, such as in this example below, where we're seeing the vertical liner wall and the moments acting upon the wall itself. All right, lastly, for structural elements, like with dynamics, we have a very in-depth number of examples, and there's certainly many more examples for how to link these structural elements to your FLAC2D grid, which is typically the case. You want to see how these support members are behaving on your model. For example, in this video here, this is a stage excavation of a tunnel where we're seeing little chunks of the tunnels being excavated, and the support members, the cables, progressing into the material, and the liner itself is modeled as beams, how the forces are distributed into these elements as the stage excavation takes place. We'll look at that one more time. This is just one very common example of what you can do with structural elements in FLAC2D. All right, and with that, that'll end the portion about structural elements. And I want to kind of change gears and talk about Python. After this, I'll briefly mention some FISH capabilities. But first, Python 3.10.5 is embedded in FLAC2D. Python offers a variety of possibilities in our code in FLAC2D. One of them is that Python may give you faster functions. If you're writing a function in FISH, the equivalent Python function is on average about 10% faster. Python also gives us the ability to do array-style programming with a module called NumPy. Array-style programming, the main concept is that you're operating on a whole list of different objects, and then rather than looping through each one and doing something to it. So there's enormous speed gains with array-style programming. We have Python modules embedded in FLAC2D. They are NumPy, SciPy, MatPy, Matplotlib, PyPy, and PySide, and many more. I won't go into the detail of each of these modules, but these are the big ones. That a question that often pops up is, what if I have my own module or another module I found on the internet that I want to use? Third-party modules can be added, but they're just not verified like our built-in modules. So what can you do with Python that is so unique? Well, for one is you can run a parametric studies quickly. And this little figure on the right here, that code, the 7 or 8 lines of code, actually runs a parametric study by changing the Young's modulus in a model from these 4 values, 6E9 to 12E9. And it runs it sequentially, where it loads the before cycling model, changes the modulus, and runs it, spits out the results, and then goes to the next one. So with FISH, this would not be possible because it does not, because on a model restore or a model new, all the information is always erased. Python, that is not the case, so it gives us the ability to run parametric studies. A couple other things you can do with Python is you can import and interpolate material properties, often done with flow pressure. You can optimize and calibrate models, and you can create custom UI or UI dialogues or wizards, commonly known as wizards. So I won't go into the building of this this UI with PySide. However, what you can see, what you can do with Python is in this top pane here, there's a bunch of Python code. Basically, what that did for me was it created my own dialog, this demo GUI, where I can specify the number of zones, the constitutive models, and assign properties. And just with each of these actions, I can create my grid, click properties, boundary conditions, and excavate, and I would do something like this. This is a very sophisticated thing you can do with Python. You have to know quite a bit about how to run Python, but it gives us this ability to, or the user the ability to make their own customized UI. Okay, that's it for Python. And then real briefly, FISH is our built-in scripting language. I'm not going to talk about everything about FISH, but rather just about this new capability in FISH, which is multi-threaded FISH. So we've added 2 concepts here, FISH splitting, and we won't go into the detail with the syntax because that's not important, but what FISH splitting allows you to do is it takes a list of all these objects, say for zones, and then it allows you to do something on this entire list, say assign a property or do something to it, rather than looping through each individual zone and doing something to it. It makes the operation run much quicker. And then in the same thread is something called a FISH operator. The FISH operator is a function that you define, and it will take these lists and it will run them in a threaded environment. So on your machine with multiple cores, multiple threads, it will run them on all threads, and your operation runs significantly faster rather than just looping on one single zone at a time. Below is an example of a FLAC2D example with about 630,000 zones, where we're just randomly changing the property, some property. And you can see on the right, using this regular loop all the way down to the fastest operation of using an operator, the time difference where using an operator is almost instant, whereas a while loop where you're doing something on each zone sequentially takes quite a bit of time. Okay, and that's it for my part. I'll hand it back off to Andre.
I will continue with the last few slides to conclude the presentation. So as you can see, FLAC2D is very flexible. It contains various modules. It contains built-in scripting language. It allows writing and running Python scripts and even bring in your own modules. It has very versatile UI, user interface. You can quickly mesh models, design them, and so on. So some other features that adds to flexibility, it's easy coupling with FLAC2D, even though license for version 9 would be required. But here's an example. So you can see how FLAC2D can be coupled with FLAC2D, and you can pretty much write code within one file that will use both PFC and FLAC2D commands. And this example shows a study of sediment deposition on very soft soil, deformable soil. So whoever runs some research studies or something more complex, this is going to be very useful for you. FLAC2D is available on both Windows and Linux platforms. FLAC2D allows running demo version with up to 1,000 zones, and you can see here on the right that you can create relatively decent model with 1,000 zones and run full FLAC2D functionality. We also allow now, or FLAC2D supports all license types, including web licensing. And FLAC2D license allows you to run FLAC 8.1 using FLAC2D license. What's coming next? Very briefly, first we're going to concentrate on adding more documentation, examples, and tutorials. We're going to continue improving user experience and user interface to make model creation and execution easier, basically adding new features in user interface. We're going to overhaul, we actually almost completed this, but it's still not publicly available, so it will be coming in future versions. Overhauled fluid logic calculations, which would be easier and faster. Implicit solutions will work even for partially saturated flow, and it will allow different permeability suction relationships. We will work on developing more tools to assist with model transfer from previous versions of FLAC, like FLAC 8.1 or earlier. We will work on more integrations with other software and vendors, and also we plan to work on developing automatic rezoning in FLAC2D, even though it's going to be quite different than in FLAC, because FLAC uses structured meshing, and we very general meshing in FLAC2D, including unstructured. And of course, we're going to add more features, whatever important going to come to our list of features, and whatever is needed for FLAC2D and for engineers. So with this, I would like to conclude presentation. I would like to thank you all for your interest and your participation in this presentation. 2 weeks trial is available to anyone registered for this webinar, so don't wait and request it today. Here are a few links that you can see for requesting 3-week trial, requesting a quote. I would also like to mention that Itasca software, there is a forum, internet forum, where users of Itasca software can discuss different topics and issues. There's also Software Academy, where people can sign up to learn, to watch or attend different online courses. And there's FLAC2D introductory course. And if you have any technical issues, you can send a question to technical support. So this is, I believe, the last slide. And with this, I would like to conclude the presentation, and we are open to questions.
Great. Thank you very much, Andre and Derek. We're a bit over time, so we'll keep it just to a few questions, and then we will follow up with your questions if we don't get it done now. So one question was, is it possible to import complex geometry from AutoCAD? Andre illustrated that in the live demo. So the answer to that is yes. Just one comment, someone is looking forward to having a Dirk theme. So if you want to add that to the development list. So a question, does FLAC2D support the C++ models available for older versions of FLAC?
Unfortunately, no. This is because they are built on different platform and different using different template. Those models will have to be rebuilt in a modern version of Visual Studio, Visual Studio 2022, I believe. However, FLAC2D provides very well-documented template for creating user-defined C++ models, and it's relatively straightforward how to do it. Feel free to go into help and just follow pretty much step-by-step guideline of how to create C++ model. And if you already have model created, you can easily recreate it for FLAC2D. And also, I would like to note that you can download Visual Studio Community Edition for free. So pretty much creating user-defined models is free. You just need to spend a little bit of time of downloading Visual Studio Community Edition and follow the guideline that's available in our help system to create your own model.
Great, thank you, Andre. And last question for today's webinar. Can we write a code in Python to build and run a model instead of FISH? If yes, do FISH operators work in Python?
In general, you can build a whole model in Python. You will probably have to run certain commands or fish from Python. Pretty much there is a way to execute commands and fish from Python. And I'm sure that there are plenty of examples in our documentation. I didn't provide any examples in this presentation, but in general, the answer to this is yes, it's doable.
Great. Thank you very much. Thank you. With that, I think we'll conclude today's webinar. There will be an email sent out to everybody who registered with information of how to find the video or recording of this webinar, get a PDF of the slide set, and also some of those links to some of those resources, including the free trial, the Software Academy, etc. And with that, we'll conclude the webinar. Thank you, Andre. Thank you, Derek. And thank you, everyone, for staying with us for the webinar.